Okay, so welcome once again to Physics Live with Ankan Bhattacharya, and you are all known to the fact that we have started the playlist of nanomaterials and applications where I usually upload the videos regarding the nanomaterials. And from the first lectures, we have discussed totally how the nanomaterials are formed, and the second lecture provide the synthesis of nanomaterials. The third lecture provide the characterization process, and today is the lecture where we have planned to deal the optical properties, as because you are all known to the fact that the nanomaterials are derived for the useful application in modern life, and as well as a wide range of application. To provide a wide range of application from the material science continuously curious to study the new particles, and the new materials called the nanomaterials uh, has derived in today's uh, environment to solve this purpose effectively. And we are all able to get some beautiful interesting phenomena from these nanoparticles that I have already discussed. And now it is the time to discuss the interesting properties that I am going to show you now. So the name of today's article is the optical properties of nanomaterials. So what do you mean by the optical property? We have some concept regarding this optical property. More simply, we can say that the color of the object is a thing, or is a wavelength of light that can be reflected from the surface of the object to our eye. Thus we get the colorization, or thus we get or recognize the color of some object. The ray of light, a wavelength of light which is reflected from the surface of the material when placed in front of our eye, and our eye recognize the color of the object by this process. The color which cannot be reflected, the objects which cannot reflect any color, is seen to be black in nature, such as black body, where the radiation fall into it, but uh, the radiation is totally absorbed. No any reflection is present there, and you have studied it while discussing the black body radiation. Okay, so this is simply what we can know about the optical property. Now what is different, or what is the new thing in the nanomaterials, is that uh, it can show a range of visible rays reflected from its surface. This is the new thing in the nanomaterials, where we get a wide range of visible ray reflecting or coming out from the nanomaterials. Now how this is possible? Let us discuss, or let us find out the fact behind it. Okay, so the nanomaterials exhibit a variety of unusual and interesting optical property that can significantly differ from that of the bulk material. That is why we are interested in nanomaterials. Okay, if I arise some example in front of you, then it will get a bit, and it will get better to understand. Okay, so take an example such as gold. Now you are all known to the fact that bulk gold appears to be yellow in color. Bulk gold appears to be yellow in color. Okay, but when you reduce the size of the gold to some 30 nanometer, of the order of 30 nanometer, then you will notice that the gold in this size reflect red light. then what will be the color of this object, or what will be the color of the gold? Then it will seem to be red. It will seem to be red, while the bulk gold was yellow. But when we reduce the size of the gold to some 30 nanometer, the gold appears to be red in color. Amazing. Let us see further. When we aggregate some nanomaterials to some bigger size, say 80 nanometer, bigger as compared to the 30 nanometer, okay? So 80 nanometer, then the gold will absorb red light, but will reflect blue light. So it absorbs red light but reflect blue light, so that the objects will be look like the object is seem to be looking like violet or purple in color. Sorry. It may be looked as purple, or it can be looked as blue in color. So from these example, you can easily find out that by reducing the size, some interesting properties arising out inside the material, which can classify them according to the color. Like similarly, you can find out that the large size zinc oxide particles block the UV light and scatter visible light, thus appearing or give it some appearance of white. But the nanosized zinc oxide particles blocks the UV light, and since they are small as compared to the wavelength of visible light, they do not scatter, so that they will look to be colorless or clear or transparent. Okay, so these are some examples. But what physical property controlling this interesting property behind the uh, nature of the nanoparticles, and how can we classify them as the basis of the color? So when you will notice 100 nanometer or something greater than these gold nanoparticles, then it will get big as compared to the 30 nanometer. Okay, and the electron cloud will simply surrounded over the surface of the atom, and this will block the photon particle to get entered or get traverse to the material, and it blocks the entry of the photon particle and totally scattered the photon particle, so that at this level the gold will appear as shiny. Okay, so the gold will appear then shiny, as because the total light is scattered back, and our eye collect the total rays of light. No ray will penetrate through the electron cloud inside the material, so that the object or the gold nanoparticles at the level of these will become shiny. Now come back to the fact that what controls these. It may be said that when the particles, let us write it so that you can remember the fact, when the particles get smaller, the electron will not be able to free okay, to about the move as about as in bulk code. So in another words, what we can say, that some quantum confinement of these electron happen there. We have studied what is quantum confinement. That is the restriction of the motion of electron within a uh, small distance or small uh, shape. That is the restriction of the motion of the quantum particle is known as the quantum confinement, and the arrangement necessary for this will get the quantum confinement conditions. Okay. So by the process, when the particles get smaller, the electrons inside it will not be able to free, will not be free as compared to the bulk gold. So the movement of the electron is restricted. Movement is restricted. So the particles uh, react differently with light. So it changes the reactivity of the material to light with light. Okay, why these different properties arising from a single material, but only changing the size of this material is laying on the fact that the particles, when get smaller, the electrons are not free to move as about in the bulk material. So the movement of the electron is restricted, and it changes the behavior of the electron towards the photon particle, and by the interaction of the electron photon you will get color different color as observed by the material at different size. So this is the main reason behind this fact. Now we can we can use this interesting property to tune our optical devices, which can react differently with different conditions by only reducing the size or by only controlling the size. So we can say what, that, let me write in red, an optical response of the nanomaterial can be created with many useful applications okay, depending on the shape, size, and arrangement. And each method may provide interesting applications or benefits depending on the target application, what we want. So let me revise what the things we have studied till now. At first I have told you, or I want to make you understand the fact that the optical property of nanomaterials is something different that is observed in bulk material. And I have arranged some example regarding it, like the gold nanoparticle and as well as zinc oxide nanoparticle, where uh, I want to make you understand that the material property gets changed while changing the size due to the quantum confinement of the quantum particles or constituting the system or constituting the materials. And in this case, the electrons are the fundamental particles that uh, control the properties arising due to the changing of size or due to the quantum confinement of it. So due to the quantum confinement, the electron changes the behavior with photon, and the interaction with the photon to the electron is very much dependent on the size of the material under the study. So size is very much essential here, and we can use this application or use this property of the nanomaterials to our target applications. What we want to make out from this. Okay, so let us proceed further. And what is the aim of this lecture? In this lecture, I will going to show you the optical process of low dimensionality structure to verify the fundamental properties of nanostructures. Okay, but the interesting fact here, the predictions derived from the energy dependence of the density of state function and the behavior of exciton in the systems of reduced dimensionality will be helpful to analyze the data in the optical properties of the nanostructure, as well as the photonic properties of low dimensional quantum structure will also be discussed in this lecture. Now I have told you I have told you some new particle, that exciton. Now what is exciton? We will shortly discuss it after few minutes. But now the thing is that the you have to study what changes gives rise to the interesting phenomena of the nanomaterials that makes some difference from it as that of the bulk material. So the first thing is that some Coulomb interaction present inside the nanomaterials. Okay, make some heading of Coulomb interaction. Coulomb interaction in the nanostructure. Now, I have already told you that in this nanostructured material, the quantum confinement effect is dominating for electron as well as holes, and the restriction of electrons and holes in some directions, let us say one dimensional d, only confinement or only quantum confinement of electrons or holes is happening in that d interval of length. This will result some quantization of energy of the amount h line square by 2 m star d square between the energy level when the electrons are arranged about the particular potential. Okay, the Coulomb interaction can result only a small correction to this energy and to this restricted motion. Now, why this quantization of energy of the order of h line square by 2m star d square occurs? Because of the quantization or because of the confinement in the length d. Because of the confinement in d length of the electrons or holes, the quantization of energy must be added to the Coulomb interaction, which is of the order of h line square by 2m star d square, but m star is the effective mass of the electron or hole under the study of the observation. Okay. Now, due to this confinement or due to this restricted motion, it can affect essentially only the motion of the remaining unrestricted degrees of freedom. Thus, the problem Okay, thus the problem of an exciton, again the word exciton comes here, I will shortly discuss. uh, Now you can imagine that exciton is nothing but some electron hole pair. Electron hole pair. Exciton is nothing but the electron hole pair. Okay, we will study in detail what is exciton, but now you can only recognize exciton as electron hole pair. So the problem of exciton due to this reduced or due to this restricted motion will be affect essentially the exciton as a bound state of electron and sorry electron and hole due to Coulomb interaction becomes low where d is equal 3 minus I dimensions. Okay, now what is I here? The number of degrees of freedom in which the free motion of electrons and holes is confined to the interval small compared to the excitonic radius, and d is the effective dimension due to this confinement. Now we will no longer use the degrees of freedom of unrestricted system. We will use the d, which is the modified dimensionality or modified degrees of freedom after the confinement. Okay, as for example, for quantum well in xy plane, if the motion of the electron or hole is governed by the Coulomb interaction, while z direction is xyz, xyz. Okay, suppose the in quantum well xy plane, the motion of electron and hole is governed by the Coulomb interaction. Okay, xy plane is governed by the motion of Coulomb interaction, while the z direction is governed by the confinement. Then the 2D Coulomb problem will give some energy of En minus or mu e to the power 4 divided by 2 epsilon square each line square n plus half that of whole square, where n is the nth state, nth energy level. Okay, for nth energy level, the energy contribution due to this confinement will modify the Coulomb 2D Coulomb problem and will gives to the correction factor of this, where mu is the reduced mass of the uh, nano device under the study. Okay, now the derivation of this energy is beyond our syllabus and I am not interested to discuss the derivation as because it is not present in our syllabus. So after certain modification regarding the condensed matter physics, you will understand how this energy have derived. So here I only want to show you the nature, in what amount of changes occur due to the energy of the Coulomb potential and not to the mathematical one. I make some stress on the physical implication of this. Okay, now the next succeeding topic of today's discussion is the plasmonic nanomaterials. What is the new thing? Plasmonic nanomaterials. What is it? Okay, so the nanoscale structure such as made of metals like gold, silver, aluminium can support surface plasmons where the free electrons, okay, let me draw some material like this, so it will have some surface plasmons. means some atoms present at the surface of these materials, which can and in the atoms there are some free electrons, that is a loosely bound electrons, which can vibrate inside the material with naturally and resonate at a frequency that depends on the composition, size and shape of the material under the study. When the incident wavelength when the wavelength of incident light matches with the oscillator frequency of these particles present at the surface, they can strongly absorb and scatter the light, resulting in a strong colored particle. It can strongly absorb and strongly scatter the incident radiation or incident visible light, so that the object will become strongly colored particle. By reducing the shape and size of these surface particles of the nanomaterials, we can tune the wavelength obtained by the reflection. Okay, so by tuning, you can say that by tuning the size and shape, the peak resonance wavelength will be shifted across the visible into the infrared region of the spectrum, electromagnetic spectrum. Okay, spectrum means the electromagnetic spectrum, allowing a wide range of color tunability. Okay, you have already studied by reducing the size, the color of the scattered wavelength or the color of the scattered light will be controlled. When the shape was of the 30 nanometer order, the gold will appear as red, but when it changes to 80 nanometer, the gold appears to be blue in color or purple. So that you can say that while controlling the shape and size of the particles, we can tune the tune the wavelength of the collected ray from the particle present at the surface of the material. Okay, this is the application of the plasmonic nanomaterials, and in this regard it is very important nowadays. Now if you want to study in detail the plasmonic nanomaterials, I can show you some important facts regarding it. Okay, so plasmonic nanomaterials, the plasmonic nanoparticles are the particles whose electron density can couple with the electromagnetic radiation of wavelength that are far larger than the particle due to the nature of the dielectric matter interface of the medium and the particles. So unlike a pure metal where there is a maximum limit on what size of wavelength can effectively couple based on their material size, what differentiates this particle from the normal surface plasmon is that the plasmonic nanoparticles also exhibit interesting scattering, absorbance, coupling properties based on their geometry's relative positions. As I have already told you, this makes some difference from ordinary metallic uh, surface particles to the surface plasmons of nanoparticles, plasmonic nanoparticles. Okay, so these unique properties have made them a focus of research in many applications, including the solar cell, spectroscopy, signal enhancement for imaging, and cancer treatment. Okay, their high sensitivity also identifies them as good candidate for designing mechano-optical instrumentations. These are some wide applications of the plasmonic nanoparticles. That is why the nanomaterial science is important nowadays. Now, what is plasmons? Plasmons are the oscillation of the free electron that are consequence of the formation of a dipole in the material due to the electromagnetic wave. Now, you have already studied the electromagnetic wave propagation throughout the plasma, and you are well aware about the condition of plasmonic frequency where the electrons oscillate if the electron or the charged particle constituting the material oscillate the frequency greater than the plasmonic frequency, then only the possible electromagnetic wave propagation will be present there. If the frequency will be less than the plasmonic frequency, then electromagnetic wave will not be able to penetrate the material, but it decays out with the material, as because in this case the damping is present because of the propagation vector to be complex or imaginary in nature. You have studied this in the electromagnetic wave paper. Okay, this is the application of the whole core branch of physics. Now the electrons migrate in the material to resonate its initial state. However, the light wave oscillate, leading to a constant shift in the dipole that forces the electrons to oscillate at the same frequency as that of the light. This is the condition of resonance. This coupling only occurs when the frequency of light is equal to the less or equal to the plasma frequency and is a greatest at the plasma frequency, that is therefore called the resonant frequency that I have already told you. The scattering and absorbance of cross sections describe the intensity of a given frequency to be scattered or absorbed. Many fabrication process of chemical synthesis method exist for preparation of such nanoparticles depending on the desired size and geometry. These things are discussed. Okay, so this is something about the plasmonic nanomaterials and surface plasmons. Now back to our discussion. So after studying the plasmonic nanomaterials, you are now well uh, informed about the application of plasmonic nanomaterials and why it is important. You can now understand it better. Okay, so now the thing which I am going to discuss you um, is about the quasi-particles. So after before the discussion of quasi-particle, let you give some time to understand the things that I have already discussed. Okay, let us start further. The new topic to be discussed is quasi-particles and excitons. Quasi-particles and excitons. So what is quasi-particles? Now it is better to told you that the idea of the quasi-particle was first originated by scientist Lev Landau's theory regarding Fermi liquid. You have studied what is Fermi gas and different thermodynamical parameter in the statistical mechanics. But sorry. I've also write the Fermi gas. It is not Fermi gas, Fermi liquid. So the idea of quasi-particle was originated in the Lev Landau's theory of Fermi liquid, which was originally invented for studying the liquid helium-3. Okay. Now let me write the definition. In physics, quasi-particles are emergent phenomena that occur microscopically complicated systems such as solids. Solid is very much complicated system. That is you have that is a thing which you have studied already in the 5th semester solid state physics, and you are very much well aware about to the fact. Now complicated systems such as solids, which behaves as if it contain differently weakly weakly interacting particles in free space. So this is the definition. In physics, the quasi-particles are the emergent phenomena that occur microscopically complicated systems such as solid behaves as if it contain differently weakly interacting particles in free space. Now, in single word, you can say that the quasi-particles are the dressed particles that originated from the real particle by some amplification of the weakly weak interactions. If I give you some example, then you will understand what I want to tell you. Okay, what I want to tell you is the thing that when a real particle is fall under the weak interaction inside a complicated system like solid, it behaves something like different. That you have already observed in the solid state physics, that when a free electron is present with mass m, the energy is continuous there, but when it is present inside the solid, it sometime due to the value of the some value of k, that is the propagation vector, it depends on the whether it behaves like free electron or whether it is behave like some tightly bound electron, or whether it is lying in between these two extreme cases. And when it is present in between two extreme cases, that is in between the free case and in between the tightly bound case, its mass gets changes to some effective mass, and we get out or we find out some uh, expression regarding the effective mass, which is nothing but 2 equal to h line square by d2v dk2. You have solved it in the solid state physics while studying the band theory. Now, what changes occurred there? due to the presence of some weak interaction or due to the presence of some interaction inside the solid, its property changes. That is, its mass changes from the real mass to the effective mass. Okay, and this differs the electron from the real particle to quasi-particle, and it is then said to be a, what is my pen? Huh. And it is then said to be the electron quasi-particle, not at all simply electron, a simple real particle. It is electron quasi-particle whose property gets changed. And in this case the energy was E to be equal to h line square k square by 2m, but here it is h line square k square by 2m star. Okay, so the property, similarly its momentum was h line k or some mv, suppose non-relativistic case. If we consider the non-relativistic case, then it is will be equal to mv, but here it will be m star v in non-relativistic case. So the physical property gets also changed due to the presence of some weak interaction there. This makes some difference from the real particle to some another particle which is known to be the quasi-particle. Another example is also studied in your solid state physics. While studying the superconductivity, you have find out the BCS theory, which was originated by Bradin, Coupard and uh, BCS Stryford in the year of 1957, where they were uh, interested mainly to discuss the reason behind the superconductivity, where they discussed that when inside the lattice, when an electron is brought there, the lattice were the lattice are connected by some elastic bonds. Okay, like this. There is also some lattice atoms, so lattice atoms are present. Positive charge center, we can assume them as to be the positive charge centers, and they are connected by the elastic bonds like this. Okay, but when some, this is also present like this, also present like this, and so on, so on. When an electron gets entered to it, it has negative charge, and attraction takes place. So the bonds gets deformed, and the new structure becomes this, these, 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 this, 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 and this. So the structure gets deformed from this state to this state due to the presence of the electron. When another electron is passed there, it makes some bond. Now you can say why there is some repulsion exists there. Yes, absolutely there is some repulsion, but the attraction due to these paired up lattice atom and electron, and to the electron, the electron lattice atom electron interaction gives out some new particle which is invisible and only present due to the physical application, which is known to be the phonon, accompanied due to the oscillation of these crystal atoms due to the presence of the electron. And this quasi-particle phonon gives rise to some attracting bond which exceeds the repulsion existing between the electron, and this makes some pair which is known as the Cooper pair, which is a class of boson of spin zero bosons due to the presence of uh, equal and opposite momentum. So spin zero bosons are known as the Cooper pairs, and due to the formation of these Cooper pairs, the electrons are free to move without any obstacles present inside the material, so the resistivity decreases, and we can easily explain the reason of the superconductivity arising out at the low temperatures of such materials like lead, uh, tin, etc., tungsten, etc. Okay, so the phonon that arising out there was also a quasi-particle. Okay, now the quasi-particles can also be called to be the collective excitations. Now you can get confused. Is quasi-particle and are quasi-particle and collective excitations are equal? Apparently equal, but there is a fine difference existing between them. When the quasi-particle, when the particles that arising out particles that arising from the fermions, they are called the quasi-particles. But when the particles deriving from the real particle, which is bosons, these are called to be collective oscillations. So this is a very fine difference, and most of the cases this difference had no meaning. So you can say that quasi-particle and collective oscillations are some equal thing. Okay. Now, what is the difference between real particle and quasi-particles? That I already pointed out, that real particles exist, move, collide and turn into one another, forming more or less complicated structures in empty space. However, quasi-particle exist, that is they move inside the macroscopic system which are construction of real particles, but they cannot be freed out. The phonon can transfer from one crystal to another, but it cannot be separated from the crystal. While we can separate out some electron or remove the electron from the crystal atom effectively, but we cannot separate the phonon from the crystal atoms. It can only transfer from one crystal atom to another, but we cannot free them, make them free, while we can get free real particles existing. Okay, this is the main difference between the real particles and quasi particles. Now our topic named as excitons. Now what is exciton? It is a very important thing to discuss. Okay, uh, excitons. I have only told you that the electron hole pair is known as the exciton. Now the exciton in detail will be studied. Let us write the absorption of photon by interband transition inside a semiconductor or insulator create an electron in conduction band and hole or the vacancy of electron in the valence band. Now these oppositely charged particles, these oppositely charged particles these oppositely charged particles attract them by Coulombic interaction. And there may be a probability of the formation of a neutral electron hole pair. This is known as the exciton. So what we have said that this is some conduction band which gets separated out from the valence band with the band gap energy some Eg. Now when some photons fall under the fall in the surface of the material, it may be semiconductor or insulator, if it gets sufficient energy or if it is able to donate sufficient energy to the electron present in the valence band that it can jumps to the conduction band, making the transition of electron from valence band to conduction band and creating a vacancy of electron in the valence band. Then these arrangement or these two particles will experience some Coulombic interaction, that is a Coulombic attraction, because these are present with opposite charges. This will experience some Coulombic interaction and preferred to be found in bonded condition or paired up condition. These electron hole pair is known to be exciton. This is not necessarily to happen, as because I have said that there is a probability of the formation. Not every time it is possible, but there is some finite probability to get the formation of this electron hole pair, and which is known as the exciton in simple language. Now the exciton, it is a very important thing to remember that exciton don't get confused with the polaron. Why? The polaron, what is polaron? Polaron is a quasi-particle. Polaron is a quasi-particle that arising from a quasi-free charge carrier such as electron or hole which moving inside a crystal with strong lattice polarization, so that the electrons or holes, the whatever we have considered here, is surrounded by some polarization cloud with an increased effective mass. This quasi-particle is known as to be polaron, which is not exciton, that is the electron hole pair. This is some polaron, so don't get confused between the two particles, exciton and polaron. Now in one sentence you can say that the basic property of the exciton is that it moves in the semiconductor but by the transportation of the excitation energy, but not at all to the charge. It has no any contribution to the transportation of charge, it has only the contribution to transportation of energy. Thus an exciton does not directly contribute to the electrical conductivity. It has no any application in the electrical conductivity. Now, depending upon these Coulombic interaction present between the electron and holes, The excitons can be classified into two classes. One is 1-year Mott excitons, and another thing is Frankel exciton. Frankel excitons. Now, what is 1-year Mott exciton? When the wave function of the electron and hole have only a slight overlap, electrons and holes have slight overlap, then it is called 1-year Mott exciton. Sorry, the hole should be represented in another color. Okay. Imagine that the blue is hole and the red one is electron. Whereas in case of Frankel exciton, the electron and holes overlap. The wave function of electron and holes gets overlap, so that there is some strong attraction between the electrons and holes present in case of the Frankel exciton, which is not present in the 1-year Mott exciton, where there is the binding energy which is very much low, of milli electron volt order. While in case of this, I can show you the data. Yes, this is the 10 milli electron volt of the order of binding energy, which is very much less as compared to this, which is 0.1 electron volt to 1 electron volt. Now, 1-year Mott excitons can be uh, explained with the help of hydrogen model. You have studied in quantum mechanics hydrogen problem. So this can be explained by the help of hydrogen model, but this cannot be explained with the help of hydrogen model. These are some basic difference between the 1-year Mott excitons and Frankel excitons. I think this lecture is too long. Yes, it is very much long, but I am not interested to go further. Just want to summarize what we have discussed, or what is the aim of this lecture series. Now, the today's topic was regarding the optical property, where we have noticed the different class of optical properties, and it originates from the difference in the size created inside the material, and an example was given. Next, we have deal some interaction present due to the confinement of the quantum particles such as electrons and holes inside the materials, and this gives rise to some contribution to the correction to the Coulomb interaction, where in one-dimensional case it is of the order of h9 square by 2 m star d square, while in case of the two-dimensional, where the Coulombic interaction was present in xy plane, but the restriction or confinement was present along z, the energy contribution was given by En as, let me box out, sorry, yes, this was the expression regarding the two-dimensional energy correction. Next, we have discussed the plasmonic nanomaterials. What are the plasmonic nanomaterials? What are the surface plasmons? And the plasmonic frequency is not described, as because it has already covered up in the electromagnetic wave lecture. Okay. Next, the thing is that we have discussed the importance of these plasmonic nanomaterials apart from the bulk plasmonic materials. Next, we have discussed the quasiparticle and the excitons. Quasiparticle was something, you can say, dressed particle. Quasiparticle can be simply said to be some dressed particle, which is made up of some real particle. We can freed up the real particle, but we cannot freed up the quasi particle present inside a material. That I have already told you. Next, the thing is that the excitons are present inside certain semiconductor or insulator, where due to the absorption of photon by the interbed transition, electron and hole pair is formed, and the excitons can be classified into two classes: Wiener mode excitons and Frankel excitons. Okay, so no more today. We will discuss the next things in the next lecture. Thank you very much.